السلام عليكم. هذا كويك overview حول استخدام design experiment أو design expert 9 software. هذا طبعا هو very important software للstatistical analysis any experimental data. Any experimental data doesn't have to be scientific, engineering, medical, could be like any statistical business, any kind of data. هو السوفتوير can be used before and after the experiment as we will see later on. هذا الويندو اللي تشوفه أول ما تفتح السوفتوير ب two options. الأوبشن الأول هو new design when we want to start a design and a model, build a new model. The second option is to edit, open and edit or extract any data from an existing model that you have already done before and you want to reuse or edit, whatever. So we will go for the first option, which is a new design now. هذا الويندو اللي راح تشوفه أول ما تفتح new design. هذا by default, comes by default. Number two هنا means, as you can see from the title on the top right, left, two levels. So هذا two levels and can deal with from 2 up to 21 factors. شنو الليفل شنو الفرق عفوا بين الفاكتورز والليفلز؟ فرضا أنا عندي experiment and دا أشتغل أنا يعني أغير بالبريشر والتمبريتشر. فعندي مثلا البريشر هذا processing parameter أو factor والتمبريتشر أيضا processing parameter أو factor. البريشر مثلا أنا دا أشتغل مثلا على 3 أو 5 أو 10 قيمة من هذا البروسيسنج بارامتر اللي هو البريشر، مثل 50 bars 100 bars 150 bars. These are levels of the same factor, same processing parameter اللي هو البريشر. Similarly للتمبريتشر، التمبريتشر نفسها processing parameter أو factor. ومثلا أنا دا أستخدم 3 قيم لهذه التمبريتشر 100 200 300، هذه levels للتمبريتشر، فهذول levels. هذا by default هذا الويندو اللي تشوفه أمامك is only for processing data extracted from two levels with different number of parameters. أنا راح أشرح واحد من الموديلات اللي هو can cover most of the experimental and research and it's very useful for people working in industry and academia and as a students. Once you get the idea how to use this software through this model that I'm going to explain later, you should be able to use all the software. It's just like different facilities, but still makes sense and still within what I'm going to explain now. طبعا هذا response surface هذا هو mainly used in يعني بالresearch بالpublication بالexperimental. Even if you work for a company and you want to design their product and optimize the processing parameter with the results, الresponse surface method الresponse surface هو يعني هو المستخدم هنا. وبعدين هذول كلهم other features يشبهوا لما أنت تروح خلالهم، لأن بس من ناحية الوقت ما أقدر أشرح كل هذول. فنروح على السيرفس response surface، وهذول هنا راح تشوف شنو الفروقات بيناتهم. راح أشرح مثلا 2. أنا راح أخذ هذا الموديل user defined. ليش؟ لأنه هذا very flex و opened. You can build it, design it according to your demand, according to your requirements in terms of input parameters and output response. البوكس banking very similar to the user defined, except one thing. When you have difficulty finding the samples, and for example أنت عندك مثلا materials is hard to find or very expensive، هذا number one. Number two مثلا أنت يكون عندك experimental work to process or produce every single sample. It could take hours or days maybe. So the experimental time is an issue here. So you go to box banking because it takes less number of samples required. So for example, if I want to build a model for 3 factors, 3 levels, that will be 3 to power 3, that's 27 samples. So in 27 samples in the user defined, but in box banking, similarly, same design, same levels and factors, it will take only 17 samples. So that's 10 samples less, and you can see how much time you can save and samples if your samples are hard to find. So we go to user defined. You can see here the minimum number of that's by default number of factors is 2, and you can start from 1 factor up to 10 factors. So I will go for 3 factors, A, B, and C, and then their levels. So I'm going to explain one experiment just hypothetically, so don't count on the numbers, don't go publish them. I'm only joking, but they are just random numbers, so they are just rubbish, nothing. So for example, I will explain laser surface hardening of metal, any kind of metal. So as long as you are working on laser, so number 1 factor is the power, units are watts, and number 2 is the frequency in hertz, and let's say here even the scanning speed or maybe the focal position is a very important factor. Sometimes in research you put the focal position over the surface, on the surface, or below the surface. So we can say focal position, it's dimensionless here. The type, as long as we are going to use levels, it's not a continuous anymore, because you are not increasing the power infinitely. You are jumping from one value to another, so it's a discrete, and discrete, because we are jumping from above the surface, on the surface, and below the surface. The levels, we said 3, 3, and 3. And here the values are coded by default between -1, 0, and 1. The idea behind this is, in case like you are working in a lab and there's some colleagues coming in and out around your computer, and you don't want anyone to know the values that you are working on. Keep them for yourself. You don't want to reveal them until you publish your work or submit it. So you use the coded values, which is -1, 0, and 1, and the values of the levels has to be equals. Like you go from 1 to 3, 100, 200, 300. You cannot like pick them randomly. They have to be equals in the graduation, if you know what I mean. So anyway, the power, like here for this experiment, I will go for 300, 400, 500, okay? And the frequency, I will use like, let's say 100, 200, 300. And focal position is going to be any values, because these are -20 means here like I'm working below the surface, 0 is on the surface, and 20 is above the surface. Any values. Now we finished inserting the input. That's only the input parameters and their levels, input factors and their levels. So we go to next step. 27 samples here I need, and then the response. The response is the output values that I'm measuring. It's the outcome of the experiment. You can see the number of samples can go, responses can go up to 999. Let's keep it simple. Go for one response, and the response is what? Surface hardness. The units, if you produce your samples and then take them to the lab and measure the hardness, as we know as engineers, we measure the hardness in even Vickers or Rockwell, or here I will use gigapascal. We finished and entering the designing the structure of the model. Here I have the full distribution of the data with the laser processing parameters, all the probabilities for the 27 samples. You can print this table, take it with you to the lab, produce all these 27 samples and make sure that you mark them so you know which is which. And then once you have your samples produced, take them again to the hardness instrument and measure your hardness and list them here. So you will be finishing all the design. So I have one design that is ready for you here, and yeah, so this is how the data look. These are the input parameters that we just finished in the next step, in the previous step, and then we just listed the output measurement, which is the surface hardness, as we agreed. Now we are ready to jump to the analysis, which is the second block on the pan on the left hand side. So go to the analysis and click on response. You would be getting this. In this window, we need to finish the setting from the left, starting from the left tab down to the right hand side to the last tab. By default, you might be like, this is the solver. This is only the way that the model is suggesting to solve the data and analyze them. But there is some terms that you have to check to make sure that your solution, your analysis is accurate. If we go to the fit summary here, just to have an idea about the analysis, here you can see up to the quadratic, it's fine, no suggestions from the model. But starting from the cubic, which is power 3, there is aliased in the data. So they might be not that accurate starting from the third degree. So we are expecting the output correlation equation is going to be maximum interaction between two factors up to the second degree. The model itself, here you have many options. We will come and play with them and see the differences. These are the solving method, different options, and also the degree of regression. Go to ANOVA table. Number one to check in ANOVA table is the model, the p-value of the model, to know whether it's significant or no. This is number one to check. Model p-value, as long as it's less than 0.05, the model is significant, and you see you have it here explained, significant. Don't mind the significancy of the parameters themselves. As long as the model itself is significant, when you have one of the parameters or all of them not that significant, or more than 0.05, that is not a problem, because it only means that this parameter within this range is not that significant, but the model is fine, so still you can use it. Scroll down. That's number one to check, is the significancy of the model. Number two to check is the R-square value. The higher the better. The closer to a unity is the better. Here I have 99.31%, which means this value, 99.31% of the data can be explained, analyzed, examined by this model, which is just perfect. When you start your first experiment and you just pick your factors and their levels randomly or close to reality, you might not be able to get this value, but from the first experiment, from the DOE 1, let's call it, you can at least identify the limits and the constraints of these values, and then do a DOE 2 which definitely will bring your results, enhance your results. So that's the R square. And then number 2 to check is the difference between the adjusted and predicted R square. The difference has to be less than 0.2. Here you can see it's within 0.1. And then the adequate ratio is number 4 to check. It has to be more than 4 according to the software recommendations. The adequate ratio is the ratio, adequate precision ratio, is the ratio between the signal and the noise. And you can see how important it is. So here it's like 5 times the recommendation, which is fine actually. And then this is a very important value that you can get, which is the equation that relates the relates the input parameters to the output response. This is the coded equation. Don't mind it. Take the actual equation. You can list it in your report, your thesis. You can even put it in an Excel sheet and test the values that you never tested in your experiment. I mean, between here we examined the power levels of 100, 200, and 300. But again, by using this equation, we can examine 150 hertz and 350 for power and so on, the values that we never tested. And confidentially, you can trust the results as long as we have these values within the limits. One thing I need to bring your attention here, you see the form of the output response. It doesn't have, the software put it in a simplest way to be presented on your computer, but it doesn't have to be like a straight direct value. Here it's the inverse of the output. So be careful. Once you calculate the value, you put the inverse for it to get the net value. Sometimes it's even more complicated than the inverse. Could be like a square root or whatever. Now we go to the next tab, the diagnostic. In the diagnostic you can check, it's very important to go to the predicted versus the actual. Here the actual value on the horizontal axis, the values that you entered, that you calculated, the values of the hardness that you entered. And on the vertical, the predicted, which can be calculated by using this equation here. So, and they are all scattered along this line. So you can see the scattered of the data is perfectly matches. So it means that your model is designed and very well designed. Number 2, actually here in the diagnostic, is to go to the box codes, which show you the 2 confidence interval. Although a confidence interval, you see between minus 1.2 and 0.32. It's nice here, the software can give you also a recommendation to even enhance and improve your analysis. So your current position, your current design for the lambda is at minus 1, and the best is minus 0.48. So this is the best, and you are here now. And it says if you go back and instead we used, I think in the solver, we used inverse. And here it gives you the recommendation to use inverse square root, which can bring the lambda to 0.5. You see the difference is not that much. So I recommend you leave it as long as you are within the limits inside the confidence interval, because if we change to a different solver, we may lose some of the accuracy here in terms of the R square or the adequate ratio or maybe the significancy of the model. So for now, we go to the last tab and get the RSM plots, which is the response surface plots. The graph you can see here show you the correlation between the power as an input parameter and the frequency with the output response, the surface hardness. This is a 2D graph. The same if you click here on the 3D, you see, this is a 3D. You can turn and swap the graph as needed to see which way you can show the variation. Okay, so these are two factors. Where's the third factor? The third factor is fixed here to show you like fixing one parameter and go all over the other two parameters. And in order to present the differences between them, you can see it's changed here. That's the third parameter, which is the focal position. Now we are expecting the hardness when the focal position is below the surface. So you see, that's for the below the surface, and then 0 is when it's on the surface. Okay, and then when it's above the surface here. In order to explain, actually, sometimes it's hard to explain. Like I think, like here, there's some hidden areas. So maybe it's better. It's up to you. I mean, if you have space in your report, you can insert both the 3D and the 2D. So you see, this is the 2D of this figure. So from here you can put your explanation. Like you can say the best hardness I could get is within this range for the power, and this range for the frequency, and this range of the focal position. Yeah, and as I said, you can insert both figures. If you right click on the figure here, actually you can manipulate all the features you have here. You can export it to any opened Word or PowerPoint document. Once you have any one opened, automatically it will go and insert it there. That's default rotation. Here you can actually play with the resolution, like x-axis. You can rename it, you can edit it anyway. The x2, which is the frequency, here you see, and the y-axis, which is the outcome, the response. Surface graph, here you can manipulate, you can edit the resolution according to your demand, and so on. You can even edit the text size and type here. You see these red spheres here, the red dots. Those are the design point. They call design point the points that you examined, your results, your actual results. But anything in between here, those are the calculated and predicted by the model itself. You never tested them, but those can be predicted by the model, as I said. If you don't like to include these design points, you still, I think somewhere here you can display vertical axis. Actually, yeah, you can somewhere here you can show design points. Here you see show design point. If you don't want them, just deselect this one, and you see they're gone. Very good feature actually. And what else okay, so this is yeah, and if you go to, this is very important actually, if you work for a company and they ask you like to give them your consultation, your advice to improve their product, if you go here to optimization, in the optimization go to numerical to get numerical values, and what we are looking for here is the output response. You see, it's by default it's on factor number 1, factor A. the factor we already identify from even a preliminary test, or from the literature, or from experience, or from trial and error. But our interest is to improve and enhance the output, which is the response, which is the hardness here. So select the surface hardness, and your goal, what is your goal? Is to maximize the hardness or minimize? Maximize or minimize? So let's say we are looking to maximize the hardness, as long as it's maximize the hardness, and then go to the solution. So if you want to maximize the hardness, you can give this report to your boss. Tell him that, okay, we didn't test this value of the power. We didn't test 473.22 watts. We didn't test frequency of 142. But you see, it give you the values in between. So are this power, this frequency, this focal position below the surface, as you can see, because it's in the negative sign. So are these, we should be able to get the maximum hardness. And if you want to make sure, just go ahead, go back to your lab, produce one sample with these parameters, produce maybe repeat it for 5. It's recommended 3 times to be repeated at least. Repeat it 3 times, measure the hardness, and find your average hardness and your standard deviation and 95 confidence interval, and give it to your boss. It should be, I don't see why not, it should be given these values of the processing parameters. So if you go through all these options here on the left hand side, it's not hard, because here I'm explaining the headlines and the main features of the software. And this is the same graph here, same graphs that we saw previously. And so one thing I'm gonna show you before I finish this video here. You see how nice the 3D and how useful it is. Beautiful. Anyway, so we go back to see the differences if we use different solver. If I think maybe by default, once you insert your data, by default, if you find it on the none, before that we did our solution and get the best results on the inverse solver. So in the transformation, if we go just hypothetically go to none and choose here anything, whichever, go to ANOVA. You see, the significance is still significant, but it's much less than what we have before. Okay, and the R square, well, it's not bad, but the difference between the two R's is more than 0.2. You see, it's about 0.36. That's out of the recommendation, but if you see, the adequate ratio is still more than 4, around the same. And here, if we go to the scatter of the data, still good. And here, well, looks maybe even better. So yeah. That's the anyway, I think that's it, and if you have any question, you may email me, and I wish you the best of luck. Thank you, and Assalamu alaikum.